May I have your attention, please? So it is now 7 o'clock, so we can get our meeting started. We've got a lot to put into tonight. For those of you who don't know me, I'm Michael Borrelli. I'm the current president, and we have several other officers here tonight. And our vice president, Shawn Hartley, and who else is here? Well, Bruce is our director, and Ed's our secretary. Absent, whatever. And then Bruce is our chairman of Outreach Committee. So we have a lot of active people. We want to have more. We want you to enjoy your club. And part of the thing we have to do tonight, because of various circumstances, we have 2 empty board seats, board of directors. And we need to vote 3 candidates for 2 positions. One of the candidates is here, Mike Huit. Mike's a longtime standing member and is looking to now serve the club on the board of directors. We have Stephen Aucoin. Some of you may not know him, but others I think all know. He's very active in the club. He's done an amazing job working with David Heagle here, doing renovations to the club, painting, and things like that. And we showed him that it's not a job that takes 80 hours a week, and he has agreed to run for the board. And the third person is a relatively new member, but extremely active, Deepak Pati. So we have only members can vote. And how many do we have who's online members? There's Deepak. Wait a minute. Well, isn't Rocky here? I thought Rocky was here. Well, that's Rocky. You're on the Zoom too. Okay. And Charles Wilmoth and Mark Dubois. All right, guys, who are on Zoom, you need to voice your opinion when we ask you who you want to vote for. So you get to vote for two people. So I'll do one at a time, and we'll see how it goes. You would want to keep a record of how many people? Okay, vote in the chat. That would be great. All right. How many of you would like to see our good friend Mike serve on the board of directors? We have 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. And you can vote for yourself, Mike. 13. No, that's my lucky number, actually. I actually won over $3,000 on a 1-3 exacta one time, many years ago. I won more on a 1-7 exacta, but that's okay. I grew up in Cherry Hill, New Jersey, which had a racetrack, Garden State Racetrack. So I used to go with my dad all the time. How'd they vote? Yeah, how many people voted for Mike? Okay, I did make the announcement. Can you guys hear me online? That we're voting votes. How many people would like to see Mike Huit vote for the board of directors? Okay, maybe a 0. Okay. All right. How many people vote for Stephen Aucoin? 1, 2, 3, 4, 5, 6, 9, 10. Okay. Stephen, 10. And how many for Deepak? Yeah, he has to put it up there. Yeah. And Deepak Pati. All right, none here. So, based on the numbers, we have 2 new board members, Mike Huit and Stephen Aucoin. And congratulations to both of you.
Michael?
Yeah?
I didn't get to vote. I was going to vote for Deepak.
Okay. Well, it still brings it up to 6, so he falls short of 13 for Mike and 10 for Stephen. Deepak, don't be disappointed. Please volunteer for other things. We'd love to have you involved. And, for example, the Outreach Committee can certainly use you beyond, I think, your beautiful imaging. And we're going to try starting an imaging workshop. John Reed and I, that's something we've been wanting to get going for a while, so we definitely need you there. Okay.
Yeah, I have no feelings. I'm fine with it. I don't mind. And I have had discussion with you, Michael. I'm
Yeah.
relatively new, so yeah, I'm fine. And if I can, yeah, I would have voted for Mike or Stephen anyway. So thank you. Thanks for the opportunity, though.
Well, we want to get you involved, especially younger
Oh
people
yes,
getting
definitely.
involved and doing things. So keep at it. And as I said, it's a good showing for the first time. All right. So we've got that business taken care of. Is there any new business before we get into our program that people want to bring up? Anything new? Bruce, you had something you wanted to talk about? You're going to hold off? If it's not going to take too long.
Number of announcements to make. Is that working for me? Yeah. First of all, I didn't have anything to do with the cowboy beans. I posted on it today only because I knew Catherine is working hard on it, and I didn't see a lot of people taking up on it, and I was afraid maybe they were worried about maybe they'd come in here and create an SO2 nebula cloud, after eating all those beans. What's the name of that cowboy movie where they're sitting around the fire, they eating their beans? What is it? Blazing Saddles. Yeah, I thought maybe people were worried about that. I don't think it works that fast, the movie notwithstanding. So, at any rate, there's that is. So, now, a little update on another matter that's not so much fun, and that is there's a lot of development planned down here around Roland, a huge amount of land that's going to be developed in a residential and probably light commercial, it looks like. I mentioned this before. We got Lakeview West to adopt some restrictions on their bill of assurance for responsible lighting, and that developer is involved in this down here. And I've talked to him about it a few months ago, and he acted like he's willing to apply those restrictions down here too. But in the meantime, this last week, I got contacted by a large, well organized group of Roland area residents that are concerned about the whole problem from a bigger perspective. And they are putting together a very impressive and complex overlay district. And they wanted my input on the lighting. So I met with them Friday. And I sent them today some proposals. A little concern about it is that as I delved into it, turns out they're concerned mostly about the ridge line. There's a certain district in there that's about the ridge line. So I had to write them today and say, no, anything we do here needs to apply to this whole area. They're just thinking about the nuisance issue, the aesthetics, and not the environmental issues aspects of it. So we'll see how that goes. I'll do my best with that. But at some point, boys and girls, there'll be public hearings, and we need people to get involved on this. We're going to have an effect in this regard. And it's a wonderful opportunity because these people are organized. If we can get them on our side and the developer's not really against what we want, maybe we can get something done down there. All right. But the main thing I wanted to talk about is as outreach chair. I've been a little slow getting some things moving. We've got a star party in next Saturday, and that has a rain date the following weekend. So if it clouds out, we will have that star party at the same location the following weekend, assuming I've got volunteers that will cover both of those dates. So this is at the soccer fields in Roland, by the way, down there by Roland, Monty Springs, actually, I think it is. What is the Natural Steps? Those soccer fields down is where we'll have it. We'll have the summer Milky Way up. Bring your telescope. But so I put out a poll, and I need everybody to respond to that poll to tell me whether you're going to make it, so I know what kind of resource I got. Now, and this is really fun to me, in addition on that poll, we've got the International Observe the Moon coming up in October. And we always have that on our outreach calendar. And the beauty of that event is you can do it anywhere. I mean, we've done it in downtown North Little Rock one time because the old moon, she sticks through. And so it occurs to me, why have just one if we can have 3 or 4 locations? I mean, this is the Central Arkansas Astronomical Society, not the Little Rock Astronomical Society. And so if we can get enough volunteers, I'd like to see us have that event in Little Rock, Conway, in the Mapleville, Benton area somewhere, probably the library in all those 3 cases. And one of our members is doing that event at Pettigene for the master naturalist. So we're just going to include that as one of our events, but he can handle that all by himself. But before we commit to some library about a partnership, we need at least 3 scopes, in my view, in Conway and in the southwest area, Bentonville, Mapleville area, and at least 4 here in Little Rock. And if we can't get that, then we'll just have to have fewer locations until we can service it. But I think that'd be a lot of fun for us to be able to sponsor 4 international Observe the Moon night locations. Now, final thing, if you are interested after this club meeting in learning to use the refractor building, come see me and we will walk you through it. We've got a video online. You can see there's a guide in the book in there, but it still is useful to walk through it physically. And so we'll do that if you want to, and we'll try to look at the moon, which unfortunately is full, but there it is. So that's all I got. Now, maybe if I could get Ed to agree to show people, because you know how to use the 14, don't you? Used to? Yeah, I don't want to try to do both, but if Ed would, if somebody's interested in the 14-inch and Ed's willing to do that, well, we'll do that too at the same time. Yeah, he uses it frequently. Yeah, but he's not here. He's in Alaska. Yeah. All right, guys. Thanks.
Our first presenter tonight is
Okay.
Darrell Heath, and he's going to share a presentation on Zoom. So I'm going to drag this over onto the screen. And Darrell, whenever you're ready.
All right. Can everyone see that?
Yep.
Okay, good. So Rocky had asked me to do a short presentation, and I had originally suggested doing a Constellation of the Month program. And then I decided against that. And the reason why was earlier this week, I had been up to the RRO. To back up a bit, I bought a Seastar S50 back in the spring, and I've been dying to use it, but due to work schedules, weather, and other conflicts of interest, I wasn't able to get out until this week to really do anything. And so I went up, even though it was a gibbous moon, I went out there and I set up and I started imaging a few things. I got some pretty good images of the Dumbbell Nebula, and I was working on the Lagoon Nebula. And I was sitting there with my iPad and I'm staring at the screen, watching it build up, the image build up. And this must have been going on for 10, 15 minutes. Then I glanced up, and out of the corner of my eye, I saw a meteor streak across the sky from out of the north. And then immediately following that, another one, but much fainter. And I realized I've been doing something that I've been preaching against for ages now. People glued to their devices, staring at their screens and not out enjoying nature and paying attention to the world around them. And I was guilty of all that. So I thought, well, why don't I do a program on at least 5 of the best summer night sky objects that you can see with binoculars. And from now, and also I want to say that I love my Seastar. I love the smart telescope idea and technology, and I think we should incorporate that into our outreach. But I hope we don't go too overboard with that. I think there's no substitute for being able to visually see things with either a pair of binoculars or through a telescope or with the unaided eye. So I'm thinking about supplementing a lot of my, if I'm doing any outreach with the Seastar, I'm going to bring along a pair of binoculars and just, get people to look at some of the easy to find objects in the night sky. But anyway, with that in mind, let's start with the first object I have here, which is the Lagoon and the Trifid Nebula, the one that I was actually staring at when I nearly missed those meteor streaks going across the sky. So here's the view on the left-hand side of the screen. You see what the trifid, or what the lagoon and trifid looks like in a pair of 10 by 50 binoculars. So yeah, you can get M8 and M20 in the same field of view. Look, it's M8 that's going to stand out the most. You're actually going to see some of the nebulosity. You don't see quite so much of that with M20 and the pair of binoculars. But I think, for my money, I think the Lagoon Nebula is the one that really shines here. Now, to find it, all you have to do is find the teapot asterism, find the spout, and just start scanning up above the spout. And of course, rising out of the spout is the summer Milky Way itself. But then you come across the lagoon and the trifid there in the same field of view. Fantastic objects to look at through a pair of binoculars and to share with other people as well. My next object, of course, is the flying duck cluster, Messier 11, which is, in my mind, one of the finest open star clusters there is. In a telescope, to me, it looks a bit almost like an open globular cluster. And in a pair of 10 by 50 binoculars, you don't quite get that sense. And you don't quite see the formation, the V formation of the stars that suggest a flock of flying ducks. But it's still a very spectacular field of view there that you get. And also, not only are you getting the stars in Messier 11, but you're getting a lot of the background stars in the Milky Way there as well. It's a beautiful sight in a pair of binoculars. Now, to find it, find the constellation of Aquila. Now, it's hard to argue against over 2,000 years of tradition, but I don't see an eagle when it's outlined like this. To me, it looks like a manta ray. So if you find the constellation there, in your imagination, draw out the wings of the eagle or the manta, and then there's a tail, a long curving tail there. And as you get down towards the end of the tail, that's where you find the wild duck cluster M11 next to Beta Scuti. So yeah, this is actually in the constellation of Scutum, the shield. All right, next object. The coat hanger cluster. In my mind, this is probably one of the finest binocular objects to look at in the summer sky. And it's called the coat hanger cluster, also known as Brocchi's cluster. It's not, the current consensus is it is not a true cluster. It's just a line of sight thing where you have various stars kind of grouped together on the sky, but they don't share any physical relationship with one another. And it does look like an upside down coat hanger. It's a startling sight and a pair of binoculars. And to find it, just go down to Albireo, and about 1.5 degrees down to the lower right from Albireo, you can find the coat hanger. And you can find it pretty much with the unaided eye. But the pair of binoculars, of course, is really going to make it pop. Of course, the finest globular cluster in the night sky, in my mind, is the Hercules cluster, M13. I'm sure a lot of you will agree with me. And a pair of binoculars is not quite as spectacular as it's going to be in a telescope view, but it's still pretty good nonetheless. Now, when Messier first formed his catalog of deep sky objects, the first catalog that he released had 45 objects in it, and he actually discovered about 17 of those. The globular cluster, Hercules cluster M13 is not one of those. This was actually discovered several decades before Messier did his catalog by Edmund Halley of Halley's Comet fame. But anyway, for a long time, I had heard that there were like 1 million stars in this globular cluster. It's actually probably about 10% of that, so about 100,000 stars. Nonetheless, it's a spectacular view in a pair of binoculars. And just think, if you were on a planet orbiting one of those stars inside M13, if there were intelligent life there, they would never know daylight. There's so many stars packed together in such a tiny volume of sky, about 160,000 light years across. But 100,000 stars packed into that tiny volume, your whole sky is going to be ablaze with light. So they would never know the universe at large. They would just see a constantly bright sky. So There you go, Bruce, an adverse side effect of light pollution there. To find the Hercules cluster at this time of the year, just look straight up and find the constellation of Hercules. Look for the Keystone asterism, and the Messier 13 is right there. Now, this is another favorite object of mine, New Draconis. It's a double star. They're not physically related to each other. At least that's my understanding. It's another line of sight thing. Some people call this the cat's eye. I don't see a cat's eye. To me, it looks like two car headlights approaching from a distance. And when you first put it up to your eyes in the pair of binoculars, it is really quite startling to see. And I highly recommend you seek that out if you've never seen it before. It's in the head of Draco the dragon. Draco's head is made up of four fairly bright stars, but the faintest star in that pattern is New Draconis, and that's where you're going to find this lovely double star. And then lastly, a few weeks ago, I took a vacation up to Boxley. This is my image of the summer Milky Way taken with my iPhone. Just scanning the Milky Way with just a pair of binoculars is always deeply rewarding. And I don't know when the last time you did that was. I did it that night in the lawn chair, just laying out in this field, looking up at the night sky. It's truly a spectacular thing to witness, just to see it with your unaided eye, but also just to scan the length and breadth of the Milky Way with a pair of binoculars. You see all kinds of nebulae and star clusters, just an amazing sight. And that's where I will stop. Rocky wanted it short, so there you have it. If you have any questions or comments, speak up. If you have any
Darrell.
mail, send that to Bruce McMath.
Absolutely. Do we have any questions for Darrell? There's not any in the classroom. Does anyone online have any questions? Alrighty. Well, thank you so much, Darrell. That's
Yep.
fascinating. I agree. There's a lot of neat things, and it's rewarding to look out with the pair of binoculars. It's the freedom, I think, not having to worry about setting things up and things of that nature. So excellent job. Thank you. All right. Next we have Jim Sykes with Mira variable class stars. Give me 1 second to get this set up. And I'll share this on Zoom. Oh, let me drag this back.
And this does what? Advance the slides. Okay. Well, good evening. We're going to look at the Mira-Class variable stars, and this is kind of how it's organized. So we'll just get started, if that works. Yeah. Or I can stand over here and punch the little button. There we go. Okay. Mira was the first variable star discovered, and it wasn't recognized as such. I noticed that Fabricus saw it on August 3rd, and it increased by 1 magnitude on August 21st. And he watched it, and then it faded in October, and he thought, well, that's a nova, which was not unreasonable. Then in 1603, when it was bright, Bayer observed it and called it Omicron Ceti, and again it faded. And then in 1638, Hawarda actually watched it for a long time and discovered that that it had a periodic brightening. Came back, he determined the period, and so he gets credited for the variability. But Hevelius is the guy who gave it its common name in his little publication there, and it is Latin. They tell me for wonderful. I don't speak Latin, so I'll have to take their word for it. Kind of do a little review here for people who aren't familiar with this diagram. The Hertzsprung-Russell diagram plots brightness or absolute magnitude against the temperature of the surface of the star. And we have a whole bunch of stars that go right through here, which is called the main sequence, and are stars which are burning hydrogen at the core. So those stars usually live a long time, and the smaller they are, the longer they live. The cool dim ones are down here, and we go up to the more massive stars and get the hot bright ones up there. When they run out of hydrogen to burn, they leave the main sequence, and some of them go up there and become Miras, and we'll talk about that. If you want to be a Mira variable, here's what you got to do. You got to have a long pulsation period. Normally, you see it greater than 100 days. I've also seen it 80 days. I don't know of any fights that have broken out over the 20-day difference, but you never know. Anyway, it can be to 1,000 or more days. It has to change in magnitude visibly by at least magnitude 2.5. They are spectral type late M, S, or C, and that's not the M you see on the HR diagram, but M indicates they're oxygen rich, the carbon rich, and S is kind of carbon and oxygen are pretty close to the same. The biggie is they have to pulse in the fundamental radial mode, which means that the whole star has to expand all at the same time and contract all at the same time. There are stars that have different times in different layers that go in and out, and also stuff that goes sideways, and those don't make it. And they are located in the late part of the asymptotic giant branch. That's the AGB, the TP, the thermally pulsing asymptotic giant branch, and we'll distinguish that from the early asymptotic giant branch as we look at things. Okay, some additional details. Most Miras start out between 1.5 and 3 solar masses. It's not a requirement, but most of them do. For various reasons, if they start out at less, the envelope's not necessarily deep enough to support the fundamental oscillation. And if they're too heavy or too massive, other things get in the way and cause them to not be Miras unless they can lose a lot of mass in the red giant branch. So generally, they lose enough mass by the time they get to be up where they could be Miras. They lose enough mass that your typical Mira will be somewhere between 1 and 1.5 times the mass of the sun. As you might expect, the pulsation is responsible for the variability of the star, but not necessarily how you might think it, and we'll talk about that. Miras, as most red giants, have deep convective cells that bring mass up from the top or from the bottom and distribute it throughout the envelope of the star. And they are big. They have significant mass loss and dust production. So if you can see this, here is Mira when it's bright, and here is Mira when it's not bright. You can see this is a lot longer exposure. And if you came up here and looked real carefully, you'd see a little red dot right there, but it's kind of hard to see from back there. So here's our stats about Mira. It is a red giant. No surprise there. All the Miras are. It has about 1.18 times the mass of the sun. It had estimated when it was back on the main sequence, when it first started out, you'll see it abbreviated ZAMS there sometimes, zero age main sequence. About 1.5 solar masses, they think, and of course it lost a lot in the red as it went through the red giant branch. As it swells and shrinks, the diameter changes between about 330 and 400 times that of the sun. And at the same time, the surface temperature changes between 3,000 and 2,600 kelvins. The magnitude, it can vary from 2 to about 10.1. It usually doesn't. It usually runs somewhere a little dimmer than 9 and somewhere up around 3 or a little less. But I've seen it up at 2, and it's pretty neat when it's up at 2. Infrared magnitude doesn't change as much, can range up to about 2 magnitudes. Pulsation period, 332 days, very irregular, you can see from the light curve here. And it's about 300 light years from us and is a binary system. It has a white dwarf binary that goes along with it about 70 AU away. Okay, some pictures. Here's Hubble with Mira and Mira B, and that's in the visible light, and here we are in ultraviolet light. The separation is only 0.6 of an arc second, and they think that Mira B is a variable or a white star, white dwarf. So here's a Chandra X-ray satellite picture, false color. The blue shows high X-ray intensity, and here's an artist's conception, which is probably not accurate. The Mira B is not close enough that Mira is going to overflow its Roche lobe like that. If it sends any matter that way, and it does send some, it's more like with the solar wind type accretion on the white dwarf. So it's not that dramatic. Here's a neat picture from the Galaxy Evolution Explorer. Mira is zipping along through the galaxy at almost 300,000 miles an hour. So it creates a bow shock wave here, you see. Notice that as it loses mass, and it loses a lot of mass, it's shedding about 1 Earth mass every 10 years. The mass is excited with the collisions with ambient hydrogen, and then it leaves a tail behind it as it goes. So it's kind of an impressive picture, I think. Okay, let's talk about what makes Mira pulse. It's called, it used to be called I believe the Eddington valve, but it's now called the Kappa mechanism. And what happens is fully ionized gas or neutral gas pretty much is transparent to radiation. In this case, we're talking hydrogen gas, and the partially ionized gas tends to block radiation, and this is how it makes it pulse. When you have the layer of hydrogen at the right depth, as it heats up, the hydrogen becomes partially ionized, which absorbs more radiation and heats up. Then this expands and it causes the whole star to expand. And then as it expands, the layer becomes cool, the ionized gas becomes neutral, releases heat, it contracts, and we do it all over again. And it takes 330 days. It's a big star, so the winds are pretty ferocious inside, and that also helps the star lose matter. Here's a schematic I did to give you an idea of the star. Here's the sun. Here's the orbit of the Earth. Here's Mars. The hydrogen layer that the ionization zone is around 30 million miles thick. And here's the surface or the photosphere of Mira when it's contracted, and here's when it's at max size. And it goes out and in 332 days. So it's got to be pretty exciting. Outside the surface of the star, there is a molecular layer, contains a lot of different atoms and molecules, and the one that we're most concerned with is titanium oxide, and we'll explain that in a minute. But this layer expands and shrinks along with the rest of the star. And it is that titanium oxide layer that causes the variability in brightness, but not necessarily how you'd think. Because when the star is at minimum, the outer layers are transparent. It goes right through them, and you see the hotter, brighter layers. So it is at when Mira is near its minimum when it is brightest. And then when it swells up, these layers cool, the atoms form molecules, they block the sunlight, a lot of the visible, and the star actually dims as it gets bigger. We know that the star is still fusing and so forth because infrared doesn't change much. But the visual magnitude, of course, can change by up to about 8. So here's a little animation of it happening. Notice that it is bright when it's smaller and dim when it's bigger. Yes. No. We will get to that. Yep, good question. Leads to the heart of the star. We'll look at that. And here it is, not in animation. We have the when it's minimum here, we have the lines of sight going right through it. At maximum size, minimum light, we have the sunscreen blocking it. So we now know why it pulses. We know why it varies. Let's look at how we get Miras and why they do what they do. So, as all stars, it starts down here on the main sequence, happily burning hydrogen. And to leap ahead and answer your question, yes, the sun can become a Mira. It probably won't, or if it does, it probably won't stay one for very long. And we'll look at why that is. Okay, after however many billion years, 10 or 12 billion years for the sun, less if you're up here, more if you're down here, we run out of hydrogen at the core. Well, when we run out of hydrogen at the core, the pressure outward ceases. And so the star starts to collapse. Well, that heats it up, and it gets hot enough that hydrogen in the shell lights off. And that, while it's doing, adds helium to this core that's already helium rich because all the hydrogen at the core made helium when it burned. Well, we're going to add more. Meanwhile, this makes the star swell and cool and move out here on the red giant branch. This can last, say, up to 1 billion years for the sun. Okay, here's our picture. We have a helium-rich core. We have a hydrogen-burning shell. We have helium being deposited, and the sun or whatever it is swells up to a red giant, maybe 100 times as big as it was. So here we go. As the helium at the core adds up and adds up, it gets more massive, it becomes degenerate. That is to say, thermal pressure cannot hold the atoms apart, and electron pressure now does. So the core is going to heat up as all this happens, and when it gets hot enough, about 100 million Kelvin, helium flash occurs. Well, you'd think that might blow the star apart, but it doesn't, because and it is releasing a lot of energy. What happens is the degenerate core sucks all that energy up and becomes non-degenerate again. Here's a picture of all that happening. We have degenerate helium, hydrogen burning. We have core ignition, and it makes the core non-degenerate. And we now have the star shrinking and becoming hotter with hydrogen burning in the shell and helium burning in the core. And these are nice, calm burns. They're nothing exciting about them. But what happens is the star shrinks now and becomes brighter. You can see it kind of becomes maybe a red or yellow giant because we're moving this way on the HR diagram. And since it shrinks but becomes brighter and getting hotter, it's kind of horizontal. So this is called the horizontal branch of the diagram. So this helium now is producing carbon and oxygen at the core. The hydrogen shell is producing helium. So it does that for a while. Here's a picture. Helium at the core, hydrogen shell, big hydrogen envelope, and whatever else it has. Okay, so there's enough, at least with the sun, and varies, of course, with the mass, but there's enough helium here in the core to last 100 million years or so. And then it shuts down. Well, now what happens is the carbon-oxygen core contracts, becomes degenerate. Gravitational energy heats around the core, and we get helium shell fusion, which goes along with hydrogen shell fusion. And the star expands and cools again and moves on to the asymptotic giant branch. They call it that because it's kind of asymptotic to the red giant branch. Okay, so we're getting closer to being a Mira, but we're not there. Here's a picture of a red giant on the AGB. We have, again, carbon oxygen core, degenerate, no fusion, helium burning shell, helium layer in here produced by the hydrogen burning shell. This star can have it swells up again, so it can have a luminosity of up to 10,000 times that of the sun. So it is a red giant, but it's, to get to your point, it's not necessarily pulsing here, or if it is, they're weak pulses. Okay, so this can occur for 1 million years or maybe up to 20 million years. The star again is swelling and moving up on the AGB. It's becoming more evolved, if you will. So this is the early AGB as opposed to the thermal pulsing AGB. Okay, so we're moving on. Here's what it looks like at the heart of the star. We have the degenerate core. We have helium shell burning. We have hydrogen shell burning. We have a bunch of intershell elements produced by helium and carbon, and we get what they call S process elements, which is S slow neutron nucleosynthesis, where an atom will capture a neutron, go through beta decay, the neutron becomes a proton, and so the element moves up one on the scale, and this is where we get a lot of the heavy elements in the galaxy. So also out here above the hydrogen shell, remember we have the convective shell that carries stuff to the surface. So here's what's happening in the early AGB. Okay, this works fine for quite a while. 1 to 20 million years. I put 5 there, but eventually that helium shell runs out. It just turns off. No gas left in the gas tank. The hydrogen shell continues to burn and makes more helium. So here's what we got. This has gone out. Everything else still going. And this really signals entry into the thermal pulsing part of the AGB, because when we get enough hydrogen here, or helium, sorry, it's going to pulse. But we don't have it yet, and it may take 100,000 years to get it. When it does, this ignites explosively now because it's a thin shell, and sends a thermal pulse out through the star and turns off the hydrogen shell, because this expands the star. This moves out. The temperature for hydrogen burning drops below where it needs to be. And so this turns off, and the convective cells can now move inward and bring up these heavy elements that are in this area, and this expands the star and deepens the envelope and brings a bunch of carbon and so forth up here. It's called dredge up, or it's, to be specific, it's called third dredge up, because there's a couple of others that can happen earlier we won't go into. Okay, here is what happens in the thermal pulse behavior, which is what's going to make our Miras, in 1.5 to 3 solar mass stars that started out that way on the main sequence. Like I say, our first wait to get enough hydrogen or helium to light off can be up to 100,000 years. And notice the helium then will only fuse for about 800 years. So what we have here is, with 100% of the time, the helium's only fusing 1% of the time or thereabouts. The hydrogen, 99%. But this helium fusion lets us dredge up a lot of carbon, a lot of other, those TiO molecules and so forth, oxygen, silicon, so forth. As it starts out, it's a shallow dredge up depth, and the pulsation is pretty irregular. These are where you get your semi-regular variables, your SRBs, your SRAs. And as we go somewhere around normally 5 to 7 pulses, we have enough material dredged up and enough envelope that we can get a fundamental pulsation behavior with the star, and that is the Mira phase. So it took us a long time, but now we're into the Mira phase, but we don't stay there too long, maybe a couple of 100,000 to 800,000 years. And then as the envelope goes off into space, we don't have enough envelope, it becomes chaotic, and we start exposing the core and moving on towards being a white dwarf. But here we are at the Miras. Like I say, it may become a Mira variable. Some little things can change it, but a lot of stars, maybe half of them become Miras at this point. Okay, just to recap there, the thermal pulse can cause a star to double in diameter over several hundred years, enriches the envelope with carbon and so forth. That's where your carbon stars come from. Thermal pulses lead to the mass loss and so forth. Okay, we're a Mira now, and Mira itself is expected to stay that way for another 100,000 to 200,000 years. Its envelope mass right now is about 6 solar masses, and when it loses about half that, it will exit the Mira phase. Mass loss continues till only the degenerate core and a planetary are left, and the core becomes a white dwarf, and that's the end of your Miras. Now, I've showed you this before, and I'm showing it to you again just so I can show you the next slide. This was our photosphere of Mira out here at minimum, at maximum, and here is the same thing I just showed you, but we've gone out and looking way back at a different word I want is anyway, we're looking at a different magnitude or wider view. There we go. Okay, here is the molecular TIO part I talked about. But outside that is the neutral gas and dust the dust formation zone, and we get a lot of grain condensation here. And then out here, up to about 3.5 billion miles from the star, we have the neutral gas and dust envelope, and you can see some of that from that Galaxy Explorer picture. The space around Mira is really cluttered with dust and gas that it has lost, and it just fades to space out here. And one last thing, if you want to look at Miras, there's a lot of them out there. The General Catalog of Variable Stars lists over 6,000. It's always some up. They don't change quickly. You don't have to look at them every night. The AAVSO would love to have your observations. You can print out charts there and compare with your comparison stars and make an estimate, and they'd love to have it. Mira is a great one because it really it's the brightest. It gets up to about magnitude 2 sometimes. And another favorite of mine is R Leo because it's pretty easy to find. There's Regulus, and Omicron's pretty bright. A couple of key stars up here that you can track on at fairly high magnitude. And the nice thing about it, when it fades to down around 10 or 11, there's some nice comparison stars in here, and it makes a nice little triangle with these two stars. It's really, really easy to follow through its whole category. That didn't work out well, but anyway, another one that two I'll mention here. With T Hercules, what I like about it is it's short, 165 days. You can follow it through. And here is R Leporus, also known as Heinz Crimson Star. Even if you don't want to follow it as a Mira, you owe it to yourself to look at this star. It is It's a carbon star. It's blood red, and it is a fascinating star to look at. I have this slide with stuff in order as a handout for anyone that wants it, in case you want to take a look at look for the Miras. And that is the end, unless there are questions. Yeah. Yeah, it's it can be pretty deep, and there's a lot of stuff. Well, yes. No, fortunately it's all the same. Yeah, it's redder, but it's the same speed. Yeah. Okay. Here's handouts if you want to pass them back. Yeah. Rocky. Yeah. It's when it's minute. Yep, and it's really red, isn't it? Yeah. And you can even, or you can ask for the light curve and see when it's going to be, maybe. Yeah. Okay. Anything else? Thank you very much for most of you staying awake. And Shawn, thank you.
Alrighty. Thanks, everybody. Big thanks to Jim Sykes. And yeah, are there any questions online? Nope. All right. Well, Michael, are you going to close us out? Okay. Alrighty. Well, that concludes tonight's presentations. Thanks everybody for attending. We're gonna gather outside and try to get in a little observing tonight. Thanks everybody for joining online, and we'll see you again next month.